Okay, welcome back. And so today we're going to continue on with a discussion with regression equations, the regression analysis. And today we're going to continue with the example that I had done before. And so let me write down that regression equation that we came up with regarding the tests. So this was the one where we had the two tests. We had the one where we had the third exam and the final. And we said, hey, can we predict a randomly chosen student's final exam score based on what they got on the third exam? And so we took the data that was given to us and we calculated the regression equation. And the regression equation that we got from the calculator was this. And so this was the equation we got. So we got that y hat, so this is the final exam score. Could be predicted, y hat, by the third exam score. And so this is the regression equation that we came up with. So this is the best regression line that maps or that models the data. Okay, so that's what we're looking at. And we also talked about how we can use this to interpret or not to interpret, but to predict certain values based on whether we're going to do interpolation, which picking an x value within the range of the x's, so the domain of the function, or whether we're going to do extrapolation where we take a value of x outside the range. And I talked about the things to consider, or the warnings when we do extrapolation versus interpolation. Okay, so now, how do we interpret the slope and the y-intercept? So we know that the definition of the y-intercept is the value of y when x is 0. And that's the mathematical definition. But how do we interpret this in the context of the problem? That's going to be the key. Okay, that's going to be important to know. Because we don't just say, well, the value of y hat is negative 173.513 when x is 0. We don't talk like that when it comes to these. Okay, the way we talk is in context. So in other words, it is true that this is the predicted value of y if x is 0, but x represents what? The score on the third exam. So what does this mean? Well, hypothetically, it means that if a student got a 0 on the third exam, he's predicted to get a negative 173 on the final exam. So if this is 0, right, this goes away, and that's what we're left with. So if he gets a 0 on the third exam, he's going to get a negative 173.513 on the final. Now, does that make sense? Does that make sense? So you always want to ask yourself, does it make sense? Does it make sense that he's going to get a negative score on the final? No. So a lot of times, depending on the context of the problem, we would change this, okay, and based on the parameters, right? But right now, that's the interpretation. So in the context of the problem, that's what you would say, okay? That would be the interpretation of the y-intercept in this case. If a student gets a 0 on the third exam, he's predicted to get a negative 173.513 on the final. Now, that doesn't make any sense, but that's what it means. Now, just for your knowledge, what we usually do when we see stuff like this, and we know that, hey, you can't get less than a 0 on either exam, okay? So what we would do is we would force our regression line to go through the origin. Because what we're saying is if you get a 0 on the final, we could predict that you'll probably get a 0 on, or excuse me, a 0 on the third exam. Maybe you'll get a 0 on the final. And even that might not hold at all. I mean, that doesn't make any sense either. Just because you get a 0 on the third exam doesn't mean that you'll get a 0 on the final. Because, you know, there's all kinds of reasons why people get zeros, right? Assuming that they took the third exam, right? Maybe they studied. But, now I'm not saying that this is a good model, but you definitely want to ask yourself questions like, does it make sense? Okay. But anyway, that's how we interpret this, the intercept. Now the slope. How do we interpret this slope? That's a little bit more difficult for students. And so what I think it's good to use are the units. I think it's very good to start with the units. Write the slope with the units. So if you want to get a good interpretation, understand this, write the units. So in other words, I'm going to take the slope and I'm going to write it out with the units. So let's first write the number. Oops. So now, what are the units of slope? Ah, that's another one. Well, what are the units of slope? Well, think of rise over run. Change in y divided by change in x, right? So it's the change in y divided by the change in x. So it's units of y over units of x, right? So in this case, we're going to do units in y over units of x. Well, what are the units of y? Your points on the final. What are the units of x? Your points on the third exam, right? So in this case, it's going to be this, right? So it's going to be, now let me do this. So in this case, the way we normally write things, right? Rise over run, so it'll be 4.827, what? Points on third exam per, right? Divided by per points on final. Okay, that's normally how we talk. So slopes represents a rate. So slope represents a rate of increase or rate of decrease. And since we're talking about a straight line, right, linear regression, it's a constant rate. So we can talk of this as 4.827 points on the third exam per point on final. Well, maybe even that's a little confusing. Well, let's write it this way, okay? Let's write it as a big fraction. So this is going to be over 1, right? So I could take any number and write it over 1, right? 4.827 divided by 1 is 4.827, right? So I can take any number and put it over 1, right? So now what I'm going to do is I'm going to put in the units. So this is points. So points on third exam over points on final. So now I have a way I can interpret this. So what does this mean? The way I interpret this, it's a rate. So the way I'm going to interpret it is, hey, for every 1 point, so again, x, the independent variable, for every 1 point I increase on the third exam, I will earn almost 5 points on the final. So for every 1 point increase in my performance on the third exam, I will increase approximately 5 points on my score on the final. That's what this is saying, okay? Now again, or you could just do a factor of 10. You could do this in many different factors, right? So I could make it out of 10 points, right? For every 10 points, and then just move the decimal point over, I could say, okay, for every 10-point increase in my grade or in my score on the third exam, I should expect to earn about 48-point increase on my performance on the final. See what I mean? So again, interpret as a rate, okay? Typically, we just put it over 1 and we just say, hey, for every 1 unit increase or 1 unit decrease, we'll do that, okay? And so that's how you interpret both the y-intercept and the slope in the context of the problem. We're going to do more of that too, but let's go on. Okay, so let me look at another example. Let's see what we got here. Okay. Hold on. Okay, let me see here. Okay, let's do another one. Okay, so here's what we're going to do. Let's do this example. So that's the data. So we're going to talk about rain versus yield for a crop. Okay, so let's look at this example. So it says, in an area of the Midwest, records were kept on the relationship between the annual rainfall in inches and the yield of wheat, bushels per acre. And so that's the data that I just showed you. So that's the sample data. So based on this sample data, we want to calculate the regression equation. Okay, so now what are you going to do? You're going to put rain in your L2 for for your X list, right? And then you're going to put in yield into your Y list or into your L2, right? So if you go to stat edit, let's do that. Okay, so stat edit, we're going to do 10.5, 8.8, 13.4, 12.5, 18.8, 10.3, 7, 15.6, 16. Okay, so now what I'm going to do is in L2, I'm going to put my Y variables. So that's going to be 50.5, 46.2, 8, 59, 4, 31.9, 76, 78.8. And you want to make sure that you put the numbers in the right order and that you don't make any typos. So now that I got both my numbers in the calculator, so now what I'm going to do is I'm going to clear out here, and now I'm going to go to Stat Tests, and I'm going to go up to linreg t-test. Why? Because it's going to give me my regression equation. And so now I'm going to go down to calculate, and what I get here is my regression equation based on the data. Okay, so now, hold on a second here. Okay, so Lindreich t-test gives me A is equal to 4.267. B is equal to 4.379. And of course, this is y hat equals A plus bx. Okay, so that's my regression line. Now, what does it say? It says, interpret the slope of the equation in the context of the given question. Okay, so here we go. So here's my regression. So my regression equation becomes, first of all, let's just write it out. So 4.267 plus 4.379 times x. Now, what does, well, let's do both. What is the, based on the context of the problem, right? X represents rainfall in inches. Y represents the predicted value of yield, wheat yield in bushels per acre. So now, what does the intercept mean? Well, the intercept means that, hey, if I get 0 rainfall, then it will predict that I will get approximately, I should predict that I'll get 4.267 bushels per acre of wheat if I get no rainfall. Okay. Now, whether that makes sense or not, probably doesn't, because if I don't get any rainfall, chances are I'm going to lose the entire crop and I'm going to end with 0. Right? I need some rain. Okay. Now, is this? I don't know if this is a particular. Yeah, this is annual rainfall, right? So it doesn't make. So if I don't get any rain for the whole season, right? Then obviously I'm not going to have any bushels per acre, right? So that might not make sense. But the main thing is the slope. So what does the slope mean? Well, in this case, the slope, let's write it out. So it's 4.379, right? Let's write it over 1. So what are the units of the top? Well, that's going to be units of y, bushels per acre, right? So the top is bushels, right? And that's per acre, so that's bushels. And the bottom is in what? Inches of rainfall. So this is inches. So we're talking about bushels over inches, right? So how do we interpret this? Well, for every 1 inch of annual rainfall, as increases, so every unit increase in inches of rainfall annually, I can expect an increase in about 4.379 bushels per acre. So again, this is bushels per acre, and this is annual inches, right? Inches per year. Okay, so again, for every 1 unit increase in inches per year, right, I will have approximately 4.379 bushels, an increase in yield of about 4.379 bushels of wheat per acre. Okay, so, and if you just want to simplify it, just bushels of wheat, right, because it's assumed to be per acre. So bushels of wheat per inch of rainfall. So bushels per inch. So for every 1 inch increase in rain, we should expect an increase in the amount of bushels per acre of about 4.4 bushels per acre. Okay? So I hope that makes sense. Okay? So let's do another one. Let's see here. Okay, let's see here. Yeah, I think that gets the point. Let me do, yeah, let me go on. Let me go on. I think that's enough. That's right. I think you guys get it. So let me see what else we need to go over. Okay, so the next thing I want to talk about is go back to correlation coefficient. So remember with correlation coefficient, we had this R value that represented the strength of the linear relationship between two variables. You know, your independent variable and your dependent variable, so X and Y. So your independent variable X and your dependent variable Y. And so this whole thing went back from scatter plots. If we see a significant relationship or a pattern with the scatter plots, then we can go ahead and calculate the correlation coefficient. And then if that correlation coefficient is significant, then we can go on to the regression part and see what is the best fit line to model the data. Okay, so now we've done all that. We've interpreted the slope, we've interpreted what the intercept means, all of that stuff, right? We've talked about predictions as far as, hey, interpolation and extrapolation and things of that sort. So let's go back to the correlation coefficient. And let's talk about something called the coefficient of determination. And so in order to talk about the coefficient of determination, the first thing that we need to talk about is variation in the y's. And so the coefficient of variation or determination, hold on a second. Yeah, the coefficient of determination measures the proportion of variation in the dependent variable y that is explained by the variation in the independent variable x. Okay, and again, that's technical terms, and I'll explain that in a minute. And what I'm gonna, and before we even show you what that means and what is denoted by that, I think it's important to understand what is the variation in the y's, because now we need to talk about what is the variation in the y's. Okay, so here's the thing. Way back when, in chapter 2, we talked about this thing called the standard deviation and variance. And variance was calculated for what? A data set. And so in a data set, we talked about how do you calculate the variance for a data set. And we came up with this formula, right? So hold on one second here. Okay. So when we talked about variance, we said, okay, if we have this X data, right? We have this data of X values. And we can calculate the standard deviation, right? Or the variance, right? And the variance was this formula, right? Oops, no square root. Was the sum of x minus x bar squared divided by n minus 1, right? And that was the calculation. That was the formula for the variance of your x's. Well, now we've got this regression equation, right? And so now we've got this prediction equation, this regression equation of y hat equals ax plus b, or excuse me, or a plus bx, right? And now we've got x and y hat, right? Or in other words, we've got this data set, right? And we've got this data set now that involves two things. We've got x values and we've got y values. So we've got all of these values, right? So we already know that in the x data set, we're going to have variation, right? And also in the y data, if we took the standard deviation of the y's, or variance of the y's, we're going to have variation there, right? And so now what we're going to do is we're going to say, well, let's calculate this variance in the y data, okay? Now, here's the formula for the variance of the y data, okay? And it's going to look very similar, okay? It's going to look like this, okay? And here we go. So the variation, so we're going to call this total variation. Okay? So total variation is equal to this. Okay? So that's a measurement of the total variation that we see in the y data. So look, it looks very similar to our calculation for the variance of x. Notice that it'd be exactly the same if we got rid of this, right? So in other words, we're just looking at the variation in the y values, okay? So this is total variation. Now, here's the thing. Because there's this relationship between x and y, right? Then it makes sense that, hey, some of that variation that we normally see in the x values, right, is probably going to translate over into the variation of the y values, right? In fact, probably a lot of it will transfer over, because if there's variation in my x data, well, then that should influence the variation in the y data if there's a relationship between the two, right? So that's where this idea where we're going to introduce now of explained variation and unexplained variation. Okay, so let me explain what that means. Okay, now the variation that we would see in the y values that is explained by the fact that we have variation in our x values. Okay, that's what we're going to call explained variation. Okay, so this is going to be explained variation. In fact, let me write this differently. So here we have, just want to make sure so if we have total variation, okay, and it's going to be this formula here, okay. I don't know if I squared that before, but it should be squared. So this is total variation. So now the next piece is going to be explained variation. So this is the variation that we would expect to see because there's variation in the x data. So that means it's explained by the variation that we see in our x data. Okay? So now, this formula for the explained variation is dependent on the model. Okay? So when we get the model, it's going to be the difference between our predicted value, okay, based on our regression equation from the mean. Okay, so here the difference is from the observed value, so y, and the mean, right? So there's the mean function, or the mean value, okay? So it's going to be the observed value minus the average or mean value, okay? What explained data is going to be the difference between the predicted value of our model, right? The difference between the predicted value, which they call, you can call y hat. I think they go back, yeah, they're using y prime. So y hat, so our predicted value, right? So it's the difference between the value we get from our regression equation, the predicted value, and y bar, the average, okay, squared, okay? So this formula gives us the explained variation, okay? Now the last one is the unexplained variation. So we have two pieces, explained versus unexplained. So here we have the unexplained variation. Now this formula is now, if this is the variation that we see in the y values that can be explained by the variation that we see in our x values, then what about the rest of the variation? Well, what is that from? Well, we don't know. That's unexplained. We don't know where that's coming from. Okay, it's coming from something other than what we can be explained by our model, by the regression line. Okay, so now this is going to be the sum of the values from where? Okay, well, this is going to be the difference between what two values? It's going to be the observed value and the predicted value. Okay, so it's going to be the difference between our observed value and y hat, the predicted value, squared. Okay, so these are the three pieces. So here's total variation. Okay, that's the variation that we see in the y data, if we have the y data, right? Has nothing to do with the model. This is just taking our sample, basically calculating the sample variance. Okay. This piece here is the amount of variation that we see in here that is explained by the model. Okay, or explained by the variation that we see in our x variable, the dependent variable, or excuse me, not the independent variable. The last piece is the unexplained variation, the variation that we see that is not explained in the model, which we don't know. This is what we call the error. Okay, this is the error part. This is the part that's explained by the model. This is the unexplained part. We don't know where it's coming. This is error. Okay. And we'll talk about error later on. Okay, so now with this here, the relationship between these three pieces is this. The total variation will always equal the explained variation plus the unexplained variation. So these two pieces should always add up to the total variation. Okay, now what does this mean? Well, R is the correlation coefficient, right? R is the correlation coefficient. Well, the coefficient of determination, or the coefficient of variation, is R squared. And so what does R squared tell you? Well, here is the definition of R squared. And it is directly related to correlation coefficient. In fact, you can derive these. But this correlation coefficient, or excuse me, the coefficient determination is equal to this. It's equal to the explained variation, right? The explained variation divided by total variation. So in other words, it's going to be this formula. The sum of y hat minus y bar squared divided by the sum of y minus y bar squared. So now here's what it means. R squared will tell you the proportion of variation, the proportion of the variation we see in the dependent variable that is explained by the variation we see in the independent variable. In other words, another way of saying it is that the proportion of variation we see in the dependent variable that is explained by our regression model. Okay, so in other words, explained by the model. Okay, so that is the definition of R squared. Okay, and typically R squared is always written as a percentage. And so what does R squared tell you? Well, here's what R squared tells you. Okay, and you'll see why it's related to correlation coefficient. R squared tells you how good your model is. So if you have a high R squared value, okay, so the closer to 100% R squared is, if you write it out as a percentage, the better your model fits the data. Okay, so the better your model is in predicting things. Okay, so in other words, R squared is a numerical or quantitative way of telling you how good your model is at predicting the y values based on your x values. Okay, so a low R squared value means that I don't have a very good model. So I don't want to probably use it for predicting things because my predictions will not be on mark. Okay, but if I have a really high R squared value, then that tells me my model is a good model and it's probably going to be good at predicting values of my dependent variable based on whatever I input in for my independent variable. Okay, so that's where I want to stop now. So again, next time we're going to come together, we're going to bring this all together and do some examples of how do we interpret this. We're going to use some examples of some data and basically take this chapter and put it all together. So see you next time and have a good day.